Hello and welcome to Measuring Water Waves. This is Waves Lesson 10, which has got the ripple tank required practical in it. My name is Mr. Pratt, Director of Science. I've done some of the previous Waves videos for you, so let's get on with it. Before we start, make sure you've got a pen, calculator, something to write on. And unless you're actually watching this video on your mobile phone, turn it off, turn it over, put it on silent. Just trying to avoid any distractions that you can avoid. So starter then, this is just recall from previous lessons. I want you to list 3 transverse waves, 3 longitudinal waves, and the wave equation with the quantities that we measure the things in. Off you go. Come up to halfway through your time. If you're super speedy, just see if you can list more than 3 of the wave types. Okay, just be quick if you haven't finished. So 3 transverse waves then, so you could have water waves, you could have any of the 7 waves from the electromagnetic spectrum, so radio, microwave, infrared, visible light, ultraviolet, X-rays, gamma rays, any 3 from that list. You could have mechanical waves on a slinky as well. So number 2, you could also have mechanical waves on a slinky because you can produce transverse and longitudinal waves with a slinky. Ultrasound and sound are the best 2 to remember for longitudinal. The wave equation, I'm not going to apologise for keep coming back to this. I'm going to ask you it several times during the course of this lesson. It's really important. It comes up a lot. So the wave equation is the velocity of the wave equals the frequency of the wave times the wavelength of the wave. Velocity would be in meters per second, frequency in hertz, and the wavelength would be in meters. Outcomes then. So first outcome, describe how the velocity, wavelength and frequency are measured using the ripple tank. So that's going to involve the wave equation. And the other outcome is to calculate the velocity of a water wave using data from an experiment. So we'll actually have some numbers, we'll have plenty of practice at using it. And also it's important if you come across a value that needs converting, for example, centimetres that need converting into metres, just we'll be doing a little bit of that, and that's important for all aspects of science, not just this lesson. We'll look at the wave equation. It's on a lot. Because it's got 2 required practicals with it, it's even more likely to be on because you'll need to use it in the required practicals. It can be quite a difficult question with the ripple tank, just because sometimes it's a little bit difficult from the question to understand what they want. But whenever you come across the wave equation being used in a ripple tank question, make sure you get the wave equation down, and we're going to be always explaining how we measure the velocity, the wavelength and the frequency. So velocity is frequency times wavelength. There's the units, meters per second, hertz and meters. You might see it in that form. So V for velocity, sometimes it will have the word speed instead of velocity in the question. Frequency F, and that's a Greek letter lambda for wavelength. We can't use W because it's already used for the units of power watts. So don't be put off by that. So shed loads of practice. So I'm going to put 5 questions here. I'm going to give you 6 minutes. If you're struggling for time, just pause it. But I'm going to just leave 6 minutes for these, and then I'm going to work through them on the visualizer so that you can mark your own and just double check that the way that you're doing it is the way that I'm doing it. It'll benefit you if you do the method in the same way as I'm doing it. So I'll give you 5 minutes with that. Okay, let's go through these questions then. So first one, what equation links frequency, velocity and wavelength? So this is just recall. Velocity equals frequency times wavelength. Doesn't ask for the units, but let's just pop them in anyway. Meters per second for velocity. Frequency is in hertz and wavelength is in meters. So question 2. A wavelength has got a frequency of 38 hertz, a wavelength of 0.18 meters. Calculate the velocity. So we don't know the velocity. We know the frequency is 38 hertz, and we know that the wavelength lambda is 0.18 meters. Velocity equals frequency times wavelength. So velocity is 38 times 0.18. 38 times 0.18. It would help if the calculator was on. 38 times 0.18 is 6.84. Three significant figures, I'll leave it at that. Underline it to point the examiner's eyes in the right place, and the units meters per second. So, question 3. Find the velocity. So we're trying to find the velocity again. The wavelength, 2.6 meters. Frequency, 460 hertz. Velocity equals frequency times wavelength, which is 460 times 2.6. 460 times 2.6. Velocity is 1,196 units. Meters per second. Underline the answer. Next, the wave's got a velocity of frequency of 9.4 hertz, wavelength 3.2 meters. Hertz, meters. Trying to find the velocity. Velocity equals frequency times wavelength. So the velocity is 9.4 times 3.2. 9.4 times 3.2 is 30.08. I don't like that because it's 4 significant figures, so I'm going to put it down to 3. So velocity equals 30.1. Units meters per second. Underline the answer. Okay, last one then. Find the frequency of a wave of wavelength 0.7 meters and speed 3.8 meters per second. So this time we're finding the frequency. So we don't know what the frequency is. The wavelength is 0.7 meters. Speed, velocity equals 3.8 meters per second. Velocity equals frequency times wavelength. Write the formula down and then we can put the numbers in underneath. So the velocity is 3.8, the frequency we don't know, and the wavelength is 0.7. So you get 1 mark for that substitution in, even if you make a bit of a mistake coming up. So make sure you do it that way. Formula, substitute what you know in underneath. So 3.8 equals the frequency times 0.7. So if we then divide both sides by 0.7, 0.7 divided by 0.7 is 1. So the frequency times 1, which is just the frequency, is 3.8 divided by 0.7. So the frequency then is 3.8 divided by 0.7, which gives us a frequency of 5.42851. I wouldn't normally write all of that out, but let's run with it. I only want 3 significant figures as a rough guide. So 5.4 So that 8's bigger than 5, so it'll be 5.43. 5.43 hertz, there's the unit. Underline the answer to draw the examiner's eye to it. So just quickly, this question would be probably worth 3. Going back to the first 4, that'll be a 1 mark. That'll be 3. That'll be 3. That'll be 3. Might be worth slightly less if they have the unit at the end of the question. Okay, let's move on. So next, let's have a look at the required practical itself. So that text there is straight out of the specification. So we can just get rid of that, because and waves in a solid I'm going to do as a separate lesson, and that's the lesson that comes up after this one. So we're not going to look at that now, we're just going to concentrate on the ripple tank. So we're going to make observations to identify the suitability of the apparatus. So really we're going to be talking about the way that we make the measurements and what we have to be careful of in order to get a bit of accuracy with the value that we find. We're going to take appropriate measurements. So the measurements that I'm going to show you how to make a frequency, wavelength and speed, and we're going to look at how we do those using the ripple tank. So we're going to use the ripple tank to measure velocity, frequency and wavelength, and then we're going to do some calculations with those. Need to be clear how we're making each measurement. Errors are very easy, and you'll see there's one measurement in particular that I do struggle with a little bit in the video. So I'm going to play this. Okay, so this is me just doing the practical at Out Academy. He's involved. We'll see how I get on.
Okay, there's 2 parts to the required practical for waves. There's a ripple tank, which I'm going to do first, and there's one with vibrations on a solid, which I'll show you second. This is quite tricky. It's tricky because the question can be slightly confusing, so I'll just introduce you to the equipment. In your lab you might have seen a smaller ripple tank. In the exam question it's generally this one. So it's a tray with about ½ centimetre of water in, legs, bulb on top. Now the important bit is it's got a motor that's suspended on rubber bands there, and you'll probably hear it, I can turn up the frequency to the motor. Turn it up. So it's vibrating, and as it vibrates, it's just rested in the water, so it's causing a ripple to go across the water. You'll see a closer view in a minute. So it's making little ripples, and I can just about see them here, but by me dangerously balancing a bulb above the ripple tank, we can see a shadow of the waves on there, and it's those that we're going to make the measurements on. So the measurements we're going to be making are all going to be on that piece of paper. And the equation that we're going to be using is the wave equation. There's probably about number 3 on the list of equations for physics. The velocity of a wave is the frequency times the wavelength. Velocity in meters per second, frequency in hertz, wavelength in meters. So as soon as you see the required practical and you see that diagram of the ripple tank, that's what you should be thinking. Okay, so with the wave equation we're going to start off measuring the velocity. So velocity, thinking back to the forces topic, velocity is distance over time. So I've already got distance marked on that piece of paper from 0 to 50 centimetres. Remember the 50 centimetres needs to be in metres, so 0.5 metres. So if I can then get a time, the velocity will be 0.5 metres divided by that time. So this is the time that the wave is taking to go from 0 to... So I'm just going to do 3 times and then I can find a mean. Ready, steady, go. 1.49, so time 1, 1.49 seconds. Reset, steady, go. Right, that looked a bit anomalous to me, but we'll write it down. 1.78 seconds. Let's see what the last one comes out at. Ready, steady, go. It's 1.88, so I'm just going to take that one out and I'll do one more. Go. Yeah, 1.79. Okay, so we've got 3 times. Let's do a mean of those. Add them all up and divide by 3. Out comes, I think, calculator. 1.78 plus 1.88 1.79 equals divided by 3. So that anomalous result had gone 1.82 to 3 significant figures, 1.82 seconds. So we've got a distance of 0.5 meters divided by 1.82 seconds. So distance divided by time, 0.50 divided by 1.82 is velocity of 0.27. I'll go to 3 significant figures, 5 meters per second. So that's V. Okay, velocity done. Next on to frequency. So frequency, definition of frequency is the number of waves in a second. So we need to know how many waves we're getting, so we can do some wave counting. And if we time how many waves we're getting in a set amount of time, then we'll know the frequency. It'll be the number of waves over the time. So what I'm going to do is, to make life simple, I'm going to time 10 seconds. And then I'm going to get the number of waves that I can get reaching the other side in 10 seconds and divide that by 10. So all I'm going to do is time 10 and count at the same time, which is easier said than done because they're not all that visible. I'm going to pick a point, I think, that is a bit more visible. It fades a bit down here, so I'm going to pick this point here where I'm going to start counting. So I'm going to click and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Right, stop. Not going to do that. I don't want to go too quick, so I'm just going to do 5 seconds instead. Struggling to keep up. Ready, steady, go. 1. Right, I'm just going to calculate that, but I'll give it another go in a minute because I'm not convinced I was all that accurate with that. So 19 waves, I reckon, divided by 5 seconds gives a frequency of 3.8. 3.8 units of frequency. So 3.8 waves in a second. No wonder I'm struggling to count them. Going to give that another go. If I do it again and I get something quite similar, I'm going to take that. I'll pick the same point. 1, 2, 3. Right, made it 20, so we'll take that. I'm not going to bother doing that calculation again. 20, 19, I'll take it. So that's giving a frequency of 3.8 Hertz. So it's velocity done, frequency done. Last one, wavelength. Don't be put off by the symbol, lambda. So it's the size of the wave from peak to peak. So if we saw it on here, it would be about there from peak to peak. But trying to measure 1 is difficult. So what we'll do is, we're going to try and mark out 10 waves along the paper. So we're going to have 10 waves. So if we find the distance of all of those 10 waves, and do distance divided by 10, we'll get the wavelength of 1 wave. So I'm going to start off 1.
Do you want me to take a photo at this point?
Yeah. Just going to take a photo, and then on the PowerPoint later I can mark it a bit more accurately than I'm doing now.
Okay.
So 3, 4, 5, 6, 7, 8, 9, 10. 10 waves in 22.5, so 22.5 centimetres, put that into metres, 0.225 metres, divided by 10 equals 0.02, I'll go to three significant figures, 25 metres, which is 2.2 centimetres, seems about right.
Just going to redo that wavelength using a still photograph, and we can see the difference that we get, and it'll give us some idea of what errors we might have had, maybe a question that comes up in there. So I've just got a still shot there with the ruler across the top. So we're going to look at the distance for 10 waves. So if I put a line marking the first one there on the zero of the ruler, so the next will be 1 wavelength, 2, 3 wavelengths, 4, 5, 6, 7, 8, 9, 10. So we've got 10 wavelengths marked on there. You'll notice that the lines that I've used to mark them have ended up not being parallel. That's because the light shining above it has made a slight angle over here where it's central in the middle of the screen. So I've just tried to mark the middle of the light band of the wave. So on that last one, so number 10, we can take a measurement from there. So 10 waves has got a distance of 0.39 metres there. So if 10 waves have got a distance of 0.39 metres, one wave will have a distance of 0.39 divided by 10, 0.039 metres. That's the wavelength. So the outline of that practical talked about understanding the suitability of the apparatus. So when we're measuring the velocity, the frequency and the wavelength, we're always talking about how we can get the most accurate values possible. Now, I'm going to look in just a second at exactly what that word accurate means, because sometimes it's used in the wrong way. So we've got a few keywords about to be revealed. And these are important because they could be asked about any of your practicals in biology, chemistry or physics. They're going to come up quite a lot. So let's try and nail using them properly and understanding exactly what the meaning is. So we've got accuracy, precision, resolution, random error, systematic error, anomaly and mean. Now I suspect you're all right with mean. You're probably all right with anomaly. Accuracy and precision you might get the wrong way around. Random error and systematic error may well be the thing that, well, it might even be new to you here, but certainly it's something that's very badly answered when I'm marking AQA exams. So accuracy then. All I want you to do, I don't expect you to write anything down. It's probably better if when we've finished going through these that you actually record what you need to record, or make a little chart like that in your book. So what I want you to do though is just for about 15 seconds now, think about if you know what that word accuracy means exactly. If something is accurate, what does that mean in a scientific context? Okay. So if you've done something accurately in science, the value that you've measured is close to the actual value. So if I go and measure someone's height in centimetres, when I've measured it, I've got a value that's very close to how tall they actually are, and I will have done that accurately. So be thinking about precision then. So I take a load of measurements, and these measurements that I take are really close to each other. Now that means that the way I'm doing the measurements is good. I'm getting them precise. I'm getting them very close to each other. So this time, let's say that I measure this same person's height and I get 115 centimetres, 114 centimetres, 114.5 centimetres. I've got the values close to each other, they're precise. Now that doesn't always mean that I'm accurate. I could have got all those readings wrong, but I've done the same thing wrong each time. So precision means getting the values close to each other, and you'd see that with repeat readings. And accuracy means getting the value that's close to the actual value. In science, what you're really aiming to do is to be precise and accurate. Resolution then. This is more to do with the thing that you're using to do the measuring. So that could be a meter ruler, so resolution. So resolution, once you've got this and it's stuck in your head, it's easy. It's the smallest measurement that an instrument could make. So if you're using a meter ruler and it's got 1 millimeter marks on it, the resolution is 1 millimeter. If you've got a stop clock and it measures to 0.01 seconds, the resolution is 0.01 seconds. If you've got a balance that measures to 0.1 of a gram, well, that's the resolution. So random error and systematic error next. I often see when I'm marking exams the phrase human error used. It won't pick your marks up on the mark scheme, although it's sort of to do with one of these next two. So random error, systematic error. See if you can think what they are. So random errors are just caused by things going wrong, and sometimes it could just be that you're doing an experiment outside and the wind changes direction, or the temperature changes, or you're doing something with a solar cell in the classroom and the sun comes out outside. So it could be anything, and these are often little environmental changes, but it could be anything. So if you're just about to write human error down in your exam, stop and just replace the word human with random and you'll pick up the marks. So with random errors, you'll get anomalies, so you'll get things that go wrong. And there was one of those on the ripple tank practical where I measured, it was when I was doing the velocity, I think one of them, the first value was wrong. Now systematic error then. Systematic error. This is more to do with the way that you've been taking the measurements or the equipment. So this is a problem with the equipment. So for example, zero error, where you've got a balance, and when you've measured out some chemicals on your balance, that it wasn't reading 0 to start with, say it was reading 0.02. So if you've got a systematic error like a zero error, it'll be there with all your readings all the way through, so it affects all your readings. So that wouldn't give you an anomaly, but it might mean that all your readings are too high, or all your readings are too low. So anomaly then, I think we're all right with anomaly. It's a reading, it's one reading that doesn't fit in with the rest. So as you're doing a practical, best practice would be just to cross that one out and do another one. Or certainly, if you're not in a position to do that, then don't include it in the mean. So the mean then, it's an average, mathematical average. You add up the number of the values that you've got, and then you divide by however many you've got. Quite often in science we'd use 3 because that's a reasonable number and it's all we have time for quite often. So what I'm going to do is, there's a series of questions here and I'm just going to give you a minute for each, and I'd like you to write these down. So question 1, when I measured the velocity I needed to find the time that one wave took to travel a certain distance. What distance did I pick? So that's a bit of memory for you, if you need to cheat and flick back to the video. And why did I pick that distance? I'll give you a minute. Okay, nearly time up for that one. Okay, don't know why bell didn't go off there. So I picked 50 centimetres, so 0.5 metres. The reason I picked that distance, I picked the biggest distance that I could, because let's say that I was 2 or 3 centimetres out. If I picked a bigger distance, it has a smaller effect on my accuracy doing it that way. So you pick the biggest distance that you can. Question 2 then. I'm not going to give you a specific time for this. Resolution of the meter ruler. I've just mentioned it about 90 seconds ago. It was 1 millimeter. So 1 millimeter was the smallest value that it could measure. So when I measured the wavelength, I struggled to get the exact starting point of the wave. So I marked it with a line, and then that was it. What sort of error would this have caused? And I tell you what, you're not writing for question 3. You're not writing human error, and I don't want you to write human error again. Okay, is it systematic or is it random? Well, it's systematic because it's always there. Once I've put that line down and I've measured to it, all my readings are effectively would be wrong, so it would affect all the readings. Question 4. The speed of the motor changed a little throughout the experiment. What sort of error would this have caused? So what you're not writing is human error. You're not writing human error. So it's either random error or systematic error. Well, that one's random error, because when you take a reading, it's just a bit of potluck on whether that motor happens to misbehave and the velocity change a little bit. Last one. That should say when I was finding the frequency by counting the number of waves in 5 seconds, I got 2 values close together. Was I being accurate, or was I being precise, or was I being both? Right, readings close together, that's good, but it doesn't mean I'm getting the right answer. So if I've got readings close together, I was being precise. Whether I was being accurate or not, well, I'm not sure what the exact value was, so I can't really be 100% positive on that. But looking at the way that I did that experiment, it was very difficult counting those waves, so I'm not sure there was a huge amount of accuracy there, but it looked like I was being precise. Okay, 1 minute, dead straightforward. This is just off an exam question there. So on that diagram, I want you to try and label parts 1, 2, 3 and 4. So I'll give you a minute. Be quick if you've not done. Okay, number 1 then, so there's your motor. Number 2, bar vibrating up and down. Sometimes it's called a dipper on some diagrams because it dips in and out of the water. 3 is pointing to the line, which represents the wave, and 4 is just the water in the ripple tank. Sometimes you'll see a diagram in the exam and it's got the bulb above it and paper underneath it. So some method questions then. first three of these are using the word describe, so you're explaining exactly how you do it, what you see when you're doing it. So we've got, you'll see the similar, I'll put the first three up. So describe how the frequency of the water waves can be measured. Describe how the wavelength of the water waves can be measured. Describe how the velocity of the water waves can be measured. So for each one, I want you to write down how I measured them. What exactly readings did I take? Did I just measure one of something, or did I do multiple amounts of something? And then at the end, 4 and 5, just a couple of conversions. So centimeters to meters and kilohertz to hertz. So I'm going to give you I'm going to give you 6 or 7 minutes for that one. Just go as quick as you can. Okay then, I'm not going to spend too long going over this for you, because actually if you struggle with your answer, your best bet is to go back to the video when I was doing the practical and just perhaps take notes on what I was doing there if you can't remember. But quickly then, frequency, I was counting the number of waves in. I ended up doing 5 seconds because 10 seconds I couldn't keep up. The wavelength, I measured the distance across 10 waves and divided by 10 to get the wavelength of 1. The velocity, you need to mention distance divided by time. So velocity is distance over time. So I measured the distance and I used 0.5 meters divided by the time. So I was timing how long the waves were taking to go across the piece of paper at the bottom. Question 4, centimeters to meters. There's 100 centimeters in a meter. So when you convert from centimeters to meters, you're going to end up with a smaller answer. So 22 divided by 100 is 0.22 meters. When you're going, question 5, from kilohertz to hertz, a kilohertz is bigger than a hertz. So you're going to end up with a bigger answer when you convert to hertz. So in my head, I would just say 1.2 thousand hertz. 1.2 thousand hertz is 1,200 hertz. A 1 mark exam question here. I'm just going to give you a minute. I'm not going to read it out because your minute includes your reading time. Okay, I'm not entirely sure that you'll need the rest of the time. So you don't need the 6 centimeters that's on the diagram. We'll talk about it anyway. The 6 centimeters on that diagram there is a measurement of 1, 2, 3 waves. So 6 centimeters for 3 waves, then the wavelength of that wave there is 2 centimeters. So question A, ripple tank produces 10 waves in 2 seconds, frequency of the waves. So frequency is the number of waves divided by the time, so that's 10 divided by 2 is 5 hertz. I prefer to see a capital H there. Bar moves faster. It now produces frequency of 20, wavelength of 0.5. Calculate the speed. Be careful because it asks for the speed in centimeters per second there. Some of you will be thinking, that's a bit easy for 3 marks. Okay, be quick if you haven't done, but I think that's a bit of a gift of 3 marks. Right, it doesn't ask for the wave equation here, but obviously you need it. So in the mark scheme, there's not going to be 1 mark for using the wave equation. So if you're stuck in an exam and you can't remember the formula for whatever reason, I'd be multiplying those 2 numbers together. And if you multiply those 2 numbers together, you're going to fall very lucky here and you're going to pick up your marks. So the frequency is 20 Hertz and the wavelength is 0.5. It wants the speed or the velocity in centimeters per second, so there's not even a conversion. So you're multiplying frequency by wavelength, because velocity is frequency times wavelength. So it's 20 times 0.2. 20 times 0.5, which is just 10 centimeters per second. An absolute gift. If you did need to do a conversion because it wanted the speed in meters per second, you do 0.5 divided by 100 first. Right, so there's a Google quiz that goes with this lesson. If you fill that in, it'll be automatically marked, so you'll get some idea about what you've done. Going to leave you with the summary then. Diagram of the apparatus, formula, wave equation there, and a little quick bit on how I measured the velocity, frequency and wavelength. So pause the video and you can make some notes to summarise this lesson. So thank you, and I'll see you next time. Next time it will be the second part of this required practical.